Hello everybody and welcome to the presentation. My name is Matthias Schneider and I will present our work in progress article Simulating Plug-in Electric Vehicle Charging for AutoML-Based Predictions of Regional Energy Demand. The authors are Sören and myself. If you have any questions, feel free to ask them after this presentation or contact us via the email addresses you find on this slide. At first, I want to introduce myself briefly. I am with Daimler TSS, which is a sub-company of the Daimler AG and is located in Ulm, Germany. We, Daimler TSS, are an in-house IT partner and provide, among others, software engineering, security, and analytics services for in-vehicle and back-end components of Daimler. I am currently working in the area of digital vehicle products. I studied computer science at the Corporate State University Baden-Württemberg and graduated last year in September. Therefore, I am all the more very excited to present you now the current state of our work. Before we start with some details, I want to give you a brief overview over the different topics we discuss in our paper and Sören and I are working on. In general, we have 4 big subjects that are addressed in the paper. As already mentioned, the main focus lies on simulating plug-in electric vehicles, abbreviated PEVs, and their charging operations. Another big part of our paper is to predict regional energy demands with the help of machine learning and especially using AutoML, which stands for Automated Machine Learning. With these predictions, it is then possible, for example, to support energy suppliers and infrastructure providers to keep the energy grid stable, even if some demand peaks happen. But more on this later on. After this little teaser, I would like to start right into the details of our work. At first, I'm going to provide you some insights into the PEV charging simulation. After that, I will touch upon the regional energy demand prediction with techniques of machine learning. In addition to that, I will present the evaluation results for both the simulation and the ML models. In the end, we conclude the presentation with a summary and a preview of what we plan to do next. So let's start with the PEV charging simulation. As a simulation approach, we choose a discrete event simulation, DES. To implement such a simulation, we decided to use SimPy, which is a Python framework for discrete event simulation. In our simulation, we have 5 major simulation entities, also illustrated on the right side of the slide. A public or home charging station comprises a number of charging points. At a charging point, only one vehicle can charge at a time. This is comparable with a gas station for vehicles with combustion engines, which also comprises several pump nozzles for the distinct cars. PEVs and charging stations are always situated at a specific location. You can think of a latitude-longitude pair here. This location will later on become very important for the predictions of the regional energy demands. Besides their current location, PEVs have a permanently assigned home location. As you can see, we are addressing the typical use case of private individuals here. Furthermore, a PEV can also be tied to a current regular or irregular tour, which in turn has exactly 2 locations, start and destination. The explanation of regular and irregular tours will follow on the next slides. For the simulation of PEVs, several reasonable assumptions had to be made based on the current practices as described in the literature and also based on our in-house experience. At first, if a PEV reaches the destination of the current assigned tour and the state of charge, the SOC, is too low to drive the next tour, the PEV will charge. Therefore, the corresponding PEV entity searches for the nearest charging station in the neighborhood. If the PEV arrives at its home location and the home location has a private charging station, the PEV will always charge, regardless of the SOC. And the third assumption we made refers to the charging behavior during a tour. Should a PEV not be able to manage the complete tour without occasionally charging, a suitable charging station or multiple charging stations are searched along the tour. In addition, we also make assumptions regarding the number and the start times of tours. However, these assumptions are freely configurable, as will be explained in the following slides. In our application example, tours to a worksite always start around 5 a.m. in the morning within a range of 3 hours. The way home is then started around 4 p.m. In the evening, another tour is made for a private drive, for example to the cinema or to sports facilities. On weekends, we assume that fewer tours are undertaken, which also start later. Since the simulation should be able to simulate a wide variety of regions, it should be possible to configure the simulation accordingly. We have 71 possible parameters with which we can adjust the simulation. In addition to static parameters such as the number of PEVs in a region, we also use normal distributions and define their means and the standard deviations in the configuration file. These normal distributions allow us to simulate, for example, the daily rush hour. Here, we then, for example, configure the mean at 8 a.m. and the standard deviation of 2 hours. The simulation can then schedule the trips for the PEVs based on these settings. After the simulation has ended, all charging operations that have taken place are written to a CSV file. Thereby, all important information concerning each charging operation is maintained. This includes, for example, the duration and the location where the charging took place. The table on the right side shows an extract of the information that is written to the CSV file. So much for the simulation. As already mentioned at the beginning of the presentation, besides the simulation of charging operations, our work also focuses on the prediction of regional energy demands. In the following slides, I would like to go into more detail about the latter. We now demonstrate the simulation's applicability. As an application example, we use the specific use case of predicting the short-term regional energy demand on the basis of the simulation output. The regions can be specific cities, for instance. As mentioned before, this can yield valuable insights for charging network operators or energy suppliers. At this point, it is important to mention that all data generated by the simulation are synthetic data. This means that no personal data will be processed, which is also an advantage of our simulation. Should personal data be used in the future to create ML models, we will only process them in compliance with data protection laws. In our application example, we simulate the city of Stuttgart in Germany for an entire year and record the charging operations. The table on the slide shows an excerpt from the data collected in the simulation. We then use this simulation output to predict short-term and regional energy demands using AutoML. However, in order to create an AutoML model, feature engineering is required first. We prepared the simulation data as follows. At first, all charging operations that occur in a given so-called partition are aggregated. A partition is a rectangle whose height and length are adjustable, what means that the number of partitions decreases or increases. Second, charging operations are aggregated by time intervals. All other values describing a charging operation, for example, the charged amount of energy in kW, are aggregated and averaged. In this application example, we use different combinations of one partition size and one time interval at each time to create several AutoML candidates. What AutoML actually is and how it differs from classic ML, I will explain in a second. As just mentioned, we use AutoML to predict the energy demands. AutoML creates ML models automatically by using dynamically selected ML techniques. The parameterization and hyperparameter optimization of the ML models is also automated. Thus, AutoML only requires a training and test datasets as input, from which an ML model is then generated. We utilized the AutoML library AutoSKLearn, which relies on the ML framework scikit-learn. Since we wanted to evaluate the performance of vanilla AutoSKLearn, we stick to use its default settings. We utilized 3/4 of the simulation output data to train the model and the remaining quarter to test it. Now that I've gone into the main details of the simulation and prediction using AutoML, I would like to present the results of our evaluations. I would like to start with the evaluation of the simulation. The simulation was evaluated using the assumptions we made earlier. For this purpose, the charts on the slide show the number of public and private charging operations during weekdays and weekend days. On a weekday around 5 a.m., private charging operations decrease noticeably, while charging operations at public charging stations increase. This is due to the fact that PVs are being driven to work sites or other locations. In the evening, the private charging operations then rise considerably, which means that the PVs are coming home again. This is also supported by the fact that public charging initially decreases during this period. The renewed increase in public charging operations in the evening suggests that tours take place again, to locations of public life and leisure. On weekends, it can be observed that there is a strong increase in home charging at around 3 p.m. This suggests that PEVs are returning from leisure trips started earlier at these times. Furthermore, it can be seen that on weekend days, less tours take place. These results are consistent with the assumptions we made. To evaluate and compare the ML models generated by AutoML, the R2 score is used. The figure on this slide shows the individual R2 values for each model. As explained earlier, one ML model was created for each of the combinations of different partition sizes and different time intervals. Here, the model with a partition size of 100 meters and a time interval of 24 hours provides the best result, 0.92. The models with the largest partition size are all not usable. Most of the other combinations provide acceptable results. After the evaluation, we now come to the end of the presentation, which I would like to finish with a conclusion. To conclude this presentation, I would like to briefly summarize the topics we have addressed in our work and the next steps we would like to take. We have developed a simulation that simulates charging operations of PEVs in a given region. This simulation is configurable with 71 parameters and thus applicable to many different problems. Using the output data from the simulation, we have trained ML models that can predict short-term and regional energy demands. The ML models were created using AutoML. In the future, we are going to further improve the simulation's underlying model so that the simulated charging operations get even better. In addition, we would like to take additional parameters into account, like, for example, the outside temperature, the battery temperature, or the PEV's charging curve. So, now we reached the end of the presentation, and I would like to thank you for your attention. If you have any questions, feel free to ask them now or contact us via the email addresses you find on the first slide. Thanks a lot.